So it's great to have Santhoshini Velusamy here for our Research at TTIC talk today. Santhoshini is an RAP with us, and actually for one more month, and then she is joining University of Waterloo as an assistant professor starting in December. And sad to see her go, but she's come back often. And today we'll be talking about relating LP relaxations, streaming algorithms, and other local algorithms for CSPs. So please.
Thank you so much, Avram, and thanks everyone for coming to my talk. So today I'll be talking about an ongoing work of mine with Madhur Tulsiani, who is also a faculty. He's a faculty at TTIC, and Noah Singer, who is a graduate student at CMU. The talk will also be based on my past works with Noah, Madhusudan, who is my advisor at Harvard, and Raghuvansh, who is a frequent collaborator of mine. Okay, so I'll define all these colorful terms because they look strange, but let's start with the strangest term here. What are these local algorithms? What do we mean by local algorithms? These are just algorithms that solve a problem by processing paths of the input locally. There are a couple of ways in which you can define locality. One is spatial locality. So imagine you have a large graph. Then you can define locality based on how far you are from certain vertices. And let's say all vertices within like radius 10 or distance 10 from you could be part of your locality. So for example, here I've just like grouped together vertices this way so that this is one group, this is another local group, and so on. And local algorithms that are based on spatial locality, basically what they do is that sort of break the whole problem into tiny pieces and only work on like each local part separately, and somehow these local pieces combine to give a global solution. That's kind of like a high-level idea. And one example of such local algorithms are distributed algorithms. Locality can also be temporal. For example, let's say you have a long stream of data, then you can define a local input based on like their arrival times. Like this set of inputs arrive in like particular time interval. This one arrives later, and so on. So you can define locality based on time. And some examples of algorithms that work based on temporal locality are like streaming algorithms, sketching algorithms, etc. These algorithms, the idea is just that they're able to like process each portion of this input locally, and then somehow only use like something they process about this input progressively to finally compute an answer. For example, here's one way you can define streaming algorithm. So let's say a streaming algorithm typically has only small amount of memory. So it can only see a given local portion of the input at a time. So let's say it looks at this portion and then produces some sort of summary of what it sees. Let's call it A. Then what it sees is that, okay, it has this summary. Then it looks at the second portion and then combines the summary with whatever input it sees and then produces another summary B, and so on. It progressively does this. And finally, whatever the summary it gets in the end is going to be its output. This is kind of the high-level structure of a streaming algorithm. Sketching algorithms are like slightly different in the sense that they have this kind of an independent structure where you don't really have to do this whole process that I mentioned sequentially. You could actually, the sketching algorithms work by, you could produce these summary sort of in parallel, and then you can combine them later. So you might wonder, like I mentioned temporal locality, so how exactly do you do these kind of things in parallel? So one could imagine, let's say, this is not like in parallel in the sense of like everything happening at the same time, but imagine there are different processors, and they all are trying to together compute some kind of, again, solve a global problem. Then they all can get like different portions of the stream at different points in time. But if you had a sketching algorithm, you can like use these sort of multiple parallel processors to work on the same problem and then produce the output later. You don't need like a single algorithm working on the entire input, for example. So anyhow, these are like some sort of high-level definitions of these different local algorithms. Why should we study these kind of local algorithms? The main motivation comes from the fact that we have massive data all around us, from applications ranging from finance, weather, social network, bioinformatics, everything produces huge amounts of data. while this data is could be as large as petabytes, the amount of readily accessible memory you have is often only in the order of gigabytes. So you cannot hope to store all this data in some central computer and then solve it by random access or whatever, which is what is typically assumed in classical algorithms. So we need to study local algorithms that sort of take this into account and process only local portions of the input and then still get some good answer to the global problem. So my research basically studies these kind of local algorithms and their interrelation. And currently I study them through the lens of so-called constraint satisfaction problems. Constraint satisfaction problems are this broad class of combinatorial optimization problems with wide-ranging applications from AI, bioinformatics, scheduling, routing, robotics, and even chip design. So there are two standard ways in which you can define a constraint satisfaction problem.
So this is a conceptual point. Can you compare it to federated learning conceptually?
Sorry, can you define?
Can you compare local algorithms to federated learning conceptually? What are the similarities and differences?
I actually don't know the formal definition of federated learning, so could you quickly tell me what it is so that I can...
So my understanding, for example, maybe we can discuss it offline more, but you are trying to train one big model from all the data, but now you have local servers to train smaller models and they communicate in some way.
Nice. Then I think if that's the case, it definitely comes under the broad picture of local algorithms. As I said, it's not a very formal definition that says only these type of algorithms can be local. Anything, as you said, I think fits in the framework of, okay, I'm going to break down my global problem into smaller pieces and then solve them and then put them together. It's a local algorithm. Thank you. Perfect. So constraint satisfaction problems, there are two ways in which you can define them. One is the search version, where at a high level, you're given some number of constraints. You're asking, is there some kind of configuration that maximizes the number of constraints you satisfy? One example is this protein folding problem, where imagine you have a long chain of amino acids, and the problem asks, what's the most efficient three-dimensional folding that minimizes energy? This can be phrased as such a constraint satisfaction problem. Another is the decision version, where now you're not concerned about finding some configuration that satisfies large number of constraints. You actually want to solve all the constraints. So basically, I give you a system, and you're asking if the system is feasible or not. These kind of decision problems are even used in chip design and stuff, where they want to check whether whatever this complex VLSI circuit they have designed, is it actually working like it's supposed to. And there are also other examples. I'm going to skip over this now. And the thing is that both these search and decision versions are hard to solve exactly. So we look for some kind of approximate solutions. For example, you could ask in the search version, can I find a configuration that satisfies, say, 90% of the maximum number of constraints? Or in the decision version, you could potentially ask, is there a configuration that satisfies, say, 90% of all constraints? All right, so that's sort of the high-level view of what are local algorithms and the constraint satisfaction problems that we're going to talk about. And here's the outline for my talk. So soon I'll define CSPs more formally and have these two examples like max cut and max die cut as sort of running examples throughout my talk. Then I'll define more formally what approximation algorithms are. Then I'll define all these three terms that you saw earlier, LP relaxation, streaming algorithms, and we will look at a specific type of local algorithms called distributed algorithms, and our conjecture that connects all the three and whatever results we have obtained so far. Finally, we'll leave you with some open problems. So constraint satisfaction problem. Formally, you have a constraint function. So it's a function that applies on k variables. That's the k over here. And each variable has a domain of size q. You can ignore these things. I just wanted to put in what we call them formally. This number of variables is called arity, and alphabet is basically the domain. But I wouldn't be using these terms too often, so if you want to forget about that, that's fine. And in general, we don't just look at a single constraint function. Usually it's a constraint family, like a family of such function. But again, for this talk, I'm going to only focus on single functions, but everything I say extends to all these families too. So here is an instance of a constraint satisfaction problem. You have a bunch of variables, let's say n variables, and another parameter m, which defines the number of constraints. Each constraint has this following structure. You pick some k variables out of these n variables and just apply this constraint function on it. What that means is that we say this constraint is satisfied. So first of all, the range of this function is just 0 or 1. And so we say this constraint is satisfied if and only if the function evaluates to 1. So that's kind of the high-level structure. Now, the goal is to find an assignment. So notice that all these variables, anyway, you want them to take value from 1 to q. You want to find some assignment such that you satisfy the maximum number of constraints. Yes.
Minor. Why is the subscript on the x and not the f?
Oh, good question. So I'm just trying to focus on a single constraint function.
Oh, that's what
right.
you said.
Yeah. So yes, you're right. In general, there is also a subscript on the f because like you can pick whichever constraint function you want in the family and then whichever variables you want to apply. Yes. Great question. Thanks.
Question.
Yes.
So the constraint function, can you put any type of function?
Yeah. Any type of function. It doesn't matter at all. You just give me a truth table, as simple as that. So it's like, it's a discrete function because the domain is discrete and range is also 0, 1. You just give me any truth table. That's a constraint function and you can define a CSP based on it.
And the constraint satisfaction problem, is that applicable for like, because I'm studying like algorithm analysis, so like analyzing for like the time complexity. Any like search algorithm, zooming algorithm, any like algorithm call, is that constraint satisfaction also applied to?
Yes, so you can define, so you're asking whether you can define algorithms for
Like time complexity.
Yeah, totally. Like people study time complexity, space complexity of like solving these problems. That's the...
So it's more universal.
Oh, so if you're asking about the complexity of the function itself, that is not something. So the function itself, we think about this q, k as some fixed constant. So it's like you give me any function, then it's just this constant size truth table that defines it. The thing that we study the complexity of is like, now when I give you some arbitrary like sort of problem with this constraint function, how efficiently can I find such an assignment? Like, how can I find such an assignment that satisfies, say, whatever number of constraints I wanted to satisfy? Does that make sense?
So the thing you're trying to get is like it's a finite constraint.
Correct. You're right. The constraint function itself is finite, but this instance need not be finite in the sense that n and m can grow arbitrarily. Like n can go to infinity, m can go to infinity. It's just that these k and q, we think of them as some fixed parameters. Perfect. Thank you so much. Perfect.
We usually assume that alphabet size in arity is a constant.
That's again a very good question. So there are, I feel like two types of literature where people also study so-called infinite domain constraint satisfaction problems and stuff like that, where Q need not be finite. But mostly in the approximation world, we study finite. Q, K are finite and fixed. But there are infinite CSPs also and whole literature around that. Perfect. Thank you. Okay, so let me give two examples of graph optimization problem and explain why they fit into this framework of constraint satisfaction problem. So here's the max cut problem where you're given an undirected graph and you're asked to like partition these vertices into two sets. So here I've denoted it by red set, blue set, partition them however you want. But the goal of this partition is so that you can maximize the number of edges that go across this red set and blue set. For example, here in this particular graph, this is the optimal partition because I'm able to capture 4 edges of the graph through this cut. This is what we call the cut of the graph. And that's the maximum because this graph is not bipartite. All right, so this is a problem clear, the max cut problem. Now, why is it a constraint satisfaction problem? So here is how you can relate it to the previous model that I described. So imagine this constraint function where your alphabet is just Boolean, 0, 1. And the constraint function just says that f of AB is 1 if and only if A is not equal to B. So if the input is 0, 1 or 1, 0, we say that the constraint is satisfied. If not, it's not satisfied. So how do we relate this constraint function to max cut? First, we define variables corresponding to all these vertices. So you have 4 vertices here, and I define x1, x2, x3, x4. Then we define constraints corresponding to every edge. So you have the edge 1, 2. I define the constraint f of x1, x2. Then you have the edge x1, x4, then f of x1, x4, and so on. Now, why is it that solving this constraint satisfaction problem is equivalent to solving max cut? The reason is because observe that this constraint is satisfied if and only if x1 is not equal to x2. We can think about this as same as 1 and 2 being placed in 2 different sets in the partition. Only if they're placed in 2 different sets, then the edge is crossing the cut. If they're placed in the same set, they're not crossing the cut. So that is kind of the analog, and which is exactly the analog. The constraint is satisfied if and only if the edges cross the cut. So if you solve this constraint satisfaction problem, you're also solving max cut. Is that clear? Okay. Max directed cut is a similar problem on directed graphs. The only difference is that now you have a directed graph. Again, I'm asking you to find a partition, but now there is a sense of direction in which the edges should be flowing. So previously we were just counting edges that were crossing the cut. Now we say that we only count edges that cross from the left side to the right side. So for example, in this case, this edge would not be counted because it's going in the opposite direction, but these other green edges are counted and the max die cut value is 3. Similar to the previous thing, you can again show that max die cut is also a constraint satisfaction problem. And the only difference would be that the constraint function, you don't say just that they're not equal. You want them to have a specific assignment. You want like a left thing to be 0 and the right thing to be 1. Or in other words, a constraint is satisfied if and only if the edge crosses the cut from a particular direction. All right, so hopefully I've convinced you max cut and die cut are constraint satisfaction problems. From now on, I'll be mainly just focusing on these 2 problems, and everything I say also just generalizes to other constraint satisfaction problems. Right. So as I said before, these problems are hard to solve exactly. Therefore, we look at like approximation algorithms for them. This is a definition of an alpha approximation algorithm. It's an algorithm. Imagine that it's a randomized algorithm. So it produces some random cut. We want it to satisfy the property that the expected value of this cut is at least alpha fraction of the optimum, which is the max cut. That is the definition of alpha approximation algorithm. So here are some trivial algorithms. Here's a half approximation algorithm for max cut. You just take every vertex, place it in the red set with probability half, or blue set with probability half. So this is just a uniform random partition of the vertices. My claim is that this partition or this cut gives a half approximation for max cut. And the reason is because the expected value of this cut is exactly m over 2. And that's because m is the number of edges. And each edge, if you're placing each of its endpoints randomly in one of these sets, the probability that the 2 endpoints lie in different sets is exactly half. So which is why the expected value is m over 2. And this is at least max cut over 2 because max cut can only be at most the number of edges in the graph. Like max cut cannot be more than the number of edges in the graph itself. So this gives a half approximation by the definition here. By a very similar reasoning, we can also show that the same uniform partition gives you 1/4 approximation for max die cut. We lose this additional factor because now you know that the direction has to be in a certain way. Previously, you can think about it like it doesn't matter where you place which endpoint, but now one endpoint has to be on one side, the other has to be on the other side, and this means that you only get a probability 1/4 of that happening. So you get a 1/4 approximation for max directed cut. Okay. Great. So these are some trivial approximation algorithms. Now I will define this notion of linear programs and linear programming relaxation. Some of you might be familiar with it, but anyhow, I will define them again. Linear programs are a very powerful tool used in combinatorial optimization. Linear programs have this like general structure where, let's say, you're trying to maximize or minimize over some linear objective, and then subject to some bunch of linear constraints. So those are, that's kind of the high-level structure of linear programs, and they are very useful. If you're able to boil your whatever problem you have down to a linear program, then there are techniques to solve these linear programs. They can be solved in polynomial time. There are several methods like ellipsoid method, interior point methods, which are probably polynomial time. There's also this simplex method, which is actually used, it is probably only exponential time, but still in practice it gives a lot more, it's much more efficient than the other method. So this is, in my understanding, is the method that's most commonly used to solve LPs in practice. But anyhow, so this is sort of the framework of linear programs. But now, how do we use this for a constraint satisfaction problem like a max cut? So let's see. So first I would write an integer linear program where I constrain all the variables I have to be integers. Then I will relax it later. So imagine having a variable z sub e for every edge e. And we say that this edge is satisfied if and only if it crosses the cut. That was our definition of like when is a constraint satisfied. Then we can also have variables corresponding to the vertices, x sub v, where let's say xv is 0 if and only if the vertex is placed in the red set. So we know that in the max cut problem, an edge is satisfied if, let's say, edge is uv. If u is placed in the red set and v is placed in the blue set, it is satisfied. Or if u is placed in the blue set and v is placed in the red set, it's satisfied. These are the only two conditions when it is satisfied. So we can try to simulate the same kind of thing using a linear program. So we want to maximize the number of constraints that are satisfied, which is just this maximize summation z sub e, and then subject to these following constraints. These are the right constraints because we don't want z sub e to take the value 1 when both xu and xv are 0 or both xu and xv are 1. That's the bad case for us because that's when the constraint is not satisfied. So if you notice that if you substitute xu, xv 0, 0, then this constraint basically says that z sub e has to be 0. Similarly, if you have xu1, xv1, this constraint would ensure that, again, z sub e is 0. On the other hand, if xu is 1 and xv is 0, you could set z sub e to be 1, which is when the constraint is satisfied. All right, so that's kind of like how we derive like the integer linear programming for max cut. But this is NP hard to solve. So while linear programs themselves are doable, when you constrain the variables to be integers, they become extremely hard to solve. So which is why we consider so-called relaxation of this LP, where instead of saying that z sub e has to be an integer which is 0 or 1, I just say it can be any fraction between 0 to 1. Similarly, the x sub v, the variables for the vertices, can again be any fraction between 0 and 1. And you write the same constraints and everything. Now this can be solved in polynomial time using the previous methods that I mentioned for LPs. Now what's the advantage of solving this problem this way? Typically what we do is like we find a fractional solution and define some suitable rounding algorithm. Rounding algorithm basically says that, okay, if you have this fraction, then you round it to an integer solution like 0 or 1 with certain probability. And that's kind of how we solve like an LP relaxation, take the fractional solution and go to a rounding thing. The thing about max cut is that, unfortunately, no matter what rounding you do, you cannot get better than half approximation. And that's kind of interesting because like half approximation is something you already get trivially by just a uniform random cut. And unfortunately, LPs don't give anything better than half. Yes?
I guess this particular LP, you can just always set all the variables to a half, like without even looking at the graph. Right?
Yes. Yes. Yeah. Yeah. That's right. Yeah. And I think that itself, that itself, I think should carry.
I guess that's not.
It is a feasible solution for sure, yeah.
I guess it's true also the random assignment also doesn't look at the graph either, right? Like you can apply that algorithm without seeing the graph.
Fair enough, yeah.
So that's kind of maybe corresponds.
Yeah, makes sense, yeah. Yeah, actually makes sense. I think all half would correspond to LP being M over 2. Let's see, what does it mean for the optimal solution?
Then you can set every z to 1 because they're all.
Oh, so you want to set all the xu's to be half so that you can set all the z's to be 1. Yeah, perfect. Yeah, okay, so what Avram was saying was just that if you look at a feasible solution, once you relax these constraints to be z fraction, xe to a fraction, without even looking at the graph, so this is like a solution just inspired by the random partition algorithm, you can set all these variables xv's to be just half. Once you set them all to just half, the constraint on ze is just that it's at most 1. So basically the LP solution gets you like m as the answer, but in the worst case, like your value could be m over 2, so you get only a half approximation from it. But yeah, so yeah, the point is that yeah, you cannot do better than half approximation for this LP. A similar LP can also be written for max die-cut. That also gives half approximation, but in this case it's non-trivial because we talked about max directed cut, where a uniform cut only gives you 1/4 approximation. So this actually does a factor 2 better than the random approximation.
Do these statements speak about integral gaps?
Oh, perfect. Yeah, this is the integrality gap statement where you cannot get better. The integrality gap is true.
Okay.
Yeah, I didn't want to use the word, but yeah, that's right. Yeah. Perfect. So I wouldn't be talking too much about what these SDPs are, but just wanted to give you a sense of like LPs are not the only thing we can do in polynomial time. We can do more complex stuff. For example, you can write so-called semi-definite programming formulation of CSPs. At a high level, you can think about this as semi-definite programs can also handle quadratic constraints, not just linear constraints. Now, the interesting thing about semi-definite programming is that you can get much better approximations for max cut using a semi-definite programming formulation. So this paper of Gomans-Williamson, which is a very celebrated paper in theoretical computer science, gave the first rounding algorithm for SDP relaxation of max cut, which achieved like 0.878 approximation. And later turned out to be the optimal approximation you can achieve in polynomial time in relation to any other polynomial time algorithms you can think of. And more interesting is that this technique of semi-definite programming relaxations can also be generalized to every CSP to obtain the optimal polynomial time approximation. Okay, but we wouldn't be talking too much about this now because our focus is on the LPs. Okay, so now I've defined CSPs formally, define what LP relaxations are. In the next half of my talk, I'm going to talk about streaming algorithms, distributed algorithms, and our conjecture connecting.
Basically, the SDP approximation is so good. What's the motivation for doing the LP approximation?
That's a very good question. I think in general, the time complexity of SDPs are like much worse compared to LPs. So there might be applications where you may not be able to even afford SDPs. So, but yeah, that's a very good question. Yeah. And there are also like, I think, a host of stuff. I mean, fair. I don't know if they can. Anyhow, yeah. So right now, I think the main class of algorithms in polynomial time for solving CSPs are LPs versus SDPs. And if you can afford the whatever polynomial factors it incurs, then you would probably use SDPs. Perfect. Thank you. Okay, so what are streaming algorithms? I mean, I already at a high level defined streaming algorithms, but again, I'll define them specifically for CSPs. So streaming algorithms for CSPs, basically the constraints arrive in a stream. Now let's just focus on max cut, die cut. In this case, edges arrive in a stream. So you don't know what the future is going to be, what the input of the graph is. It's one by one, the algorithm sees an edge, for example. It just process it like in this animation. An algorithm sees the edge exactly once. You cannot sort of go back to, unless you store that edge specifically, you can't go back and access it. That's kind of the point. And the resource constraints that we think about in such a model is typically just the space. the time is unconstrained. And in my understanding, the motivation is because usually it's much more expensive to, let's say, access something from an external memory or even something outside your cache versus like just local processing time and compared to local processing time. These times, even if they're counted as like one time step, actually the number of cycles it takes to access a memory versus your processing cycles for doing some addition or multiplication is going to be very different. So I think the motivation here is that let's say you have very limited space, that means you can access the memory like super fast, then it really doesn't matter how much time you're taking. That's kind of was the motivation, I believe, to not constrain time. And this is what we will be working with. But interestingly, because time is unconstrained, naturally what happens is that if you give large enough space, you should be able to do something much better than polynomial time algorithms, for example. So here, if I give you order n space, where n is the number of vertices, then I can even get like 1 minus epsilon approximation for any epsilon. So this is almost like as good as like exactly solving the problem. On the other hand, we saw that these SDP-based approximations don't get you anything better than this 0.878 approximations for max cut. So in that sense, this model, like once you don't constrain time, if you allow a lot of space, you're going to expect to actually solve the problem entirely. So, and this algorithm it's a very simple algorithm. You sample a bunch of random edges, like n over epsilon square random edges, and just estimate max cut based on all the edges you sample, and it turns out that this is sufficient to get the 1 minus epsilon approximation. So I would say the interesting space regime in this streaming model is when your space is little o of n, because if it's order n, you're able to do everything. So what can we actually do in little o of n space? Little o of n just means like any function that grows smaller than n. It could be n to the half, n over log n, whatever it is. But yeah, just for those not familiar with the notation. All right. One more thing, if you notice, is that when you say little o of n space, that means that you don't even have enough space to output the cut. A cut is defined by 2 to the n possible partitions. So if you're going to represent a cut, you need at least n bits of information because you have 2 to the n different possible inputs. So once I restrict you that you can only use little o of n space, there is no hope to even output the cut. So the problem definition slightly changes in the sense that we say an algorithm is alpha approximation algorithm if it's only estimating the value of the best cut, not actually outputting it. So you're only asking for a value v, not actually a cut, such that this value is at least alpha fraction of this max cut. And we also want it to be at most max cut because if you don't have this constraint, I can, output infinity, and that's always going to satisfy this constraint. Okay. Any question? Yes.
In practice, why would you want to know the value but not know the cut?
I think this would be very helpful. Like, let's say if you have a constraint system where you want to just know, can I satisfy like 99% of the constraints or something? So this would be very useful in those kind of approximate decision problems where you can use a streaming algorithm and check whether it's satisfied. Exactly. Perfect. So this is our conjecture with Madhur and Noah Singer in our current paper where we say that the best single-pass streaming approximation you can achieve in little o of n space is same as the approximation achieved by LP relaxation for any CSP. So our conjecture is that whatever LPs are capable of is exactly what streaming algorithms are capable of in little o of n space. I say it's a conjecture because we don't have a proof yet, but what we have managed to prove so far is that if you look at streaming algorithms in little o of square root of n space, then that approximation is weaker than what you can do with LP relaxations. And there are also some evidence showing that whatever LP relaxation can do, we can come up with algorithms that can actually do it in streaming. Okay. So I wouldn't prove this result here, but again, I want to give you some intuition for why streaming is not more capable than LP. Later, I will tell you about why it's at least as capable as LP, but now I'm just going to tell you why it's not more capable than LP. And the first example we could think of is the max cut problem. We said that LPs can do nothing with that. Like literally, you can get only half approximation and nothing better. That is also true in streaming. And this is the paper that showed that. So this is a paper by Caprillo and Crutchon, where they showed that they can construct graphs whose max cut value is 1, or in another sense, they're just perfect bipartite graphs, versus a random graph which has max cut value around half. And they show that streaming algorithms cannot distinguish between these two. At a high level, the way they show is that somehow the graphs they construct have this nice form where you can decompose them into these tiny matchings. And what they do is they send edges from a matching at a time to the streaming algorithm. So how do you differentiate a graph that has max cut value 1 from half? Only if you see some odd cycle. Because if a graph is bipartite, you won't see any odd cycle, in which case max cut value will be 1. And if it's not 1, then it should have a cycle. And their idea is that because you're only seeing some matchings at a time, unless you know, you don't know where the cycle is hiding. Here, the cycle is hiding right here, but that's very hard to know when you only see one of these edges at a time. So unless somehow you remembered like order n edges, you won't be able to detect odd cycle. That sort of is the high level idea and shows that for max cut, you don't have better than half approximation. And their same result also extends to max die cut. And the reason is because you just take this instance, add some random directions to these edges. That doesn't change the hardness of the problem. But now when you add random directions, originally this was max cut 1, all the edges just crossed. Now when you add random directions, half the edges are going to cross in the correct way you want. So roughly the max die cut is half. Similarly, when max cut is half, now die cut becomes 1/4 because again, half of those edges cross in the correct directions you want. Anyhow, so again, the ratio of these max die cut value is like 2. So this also shows that for max die cut, yes.
Just a question. So what if you're dealing with graphs that are much more complex, bigger in size?
Very good question.
How do you use the partitioned graph to be so that it's more, because those examples kind of look more even, but if the graph is much larger in size, then how do you get it to be symmetrical in the partition?
That's a really good question. So this lower bound is like just saying that, hey, here, like you cannot have a very generic algorithm that solves all kinds of graphs, because here is an example of a graph you can't solve it for. But your question is very good in the sense that if you have very dense graphs, let's say that my graph has n square edges, bigger graph, dense in the sense of like n vertices, n square edges, you can actually solve max cut using just constant space. Like these are algorithms where there are even so-called property testing algorithms where I can just query a few edges, a constant number of edges in the graph, and then I'll be able to tell you what its max cut value is.
Like you have to individually count all the edges, not the edges, all the vertices.
So what I mean by constant is just like, let's say I'm looking for 1 minus epsilon approximation. I would call, if I'm querying anything like 1 over epsilon or even 2 to the 1 over epsilon, that would be a constant for me. Because it's like, let's say I want 0.99 approximation for max cut, and I have a very dense graph which has like n square edges, then I only need to maybe query like, 10,000 edges or 100,000 edges. It's independent of n itself. N can be 5 billion, I don't care. But the number of edges I'm going to query is independent of n, which is like 10,000 edges. Some fixed number of edges I need to query, and then I can tell you max die cut. So when graphs are actually very dense, you can do wonderful stuff to them.
Just to look at that, so the 10,000 vertices that you have in your graph, you then try to partition it. What you were talking is you just split them.
So good point. Sorry, I'll take that back. So I'm considering like computing the value now. So I'm not actually computing the cut. So of course, like as I said before, if you're trying to like compute a cut itself, somehow you need like that n space. Like n is the number of vertices. There is no way of getting rid of it because like your partitions itself is like 2 to the n partition. So you need that n space. Now we are at this problem where you're only trying to find the value of the largest cut. So in the sense of like, let's say my graph has like 50,000 edges. I want to know like what fraction of those edges can I make them cross the cut? Is that graph bipartite in the sense that can I somehow make all the edges cross a cut, or can I make half the edges cross a cut, 3/4, whatever. So this number,
So you're just picking a section.
I'm literally only worried about the number. How good is this graph in terms of its max cut value? I'm only trying to estimate the value of it, but not actually output the cut. Exactly. I'm not trying to. So I'm still trying to estimate something on the global thing, but not actually outputting where you have to place each vertex. Just saying that there must exist some partition such that, let's say, I can satisfy 80% of the edges can be in this cut, but I'm not telling you what the cut itself is.
Okay, so it would basically depend on, the size of the graph.
Exactly. If you're trying to actually find the whole cut, the complexity would have to depend on the graph itself. The novel thing about this is just that when you're sort of not looking to output the cut, it's like question similar to what Matt was asking in terms of why would you use such a thing? So let's say you have a bunch of constraints and you want to just know, okay, is this even, in the best case, it's like this VLSI kind of thing where you want to know if everything is working as it's supposed to be. You give me a circuit, can I just tell if all the constraints are satisfied or not? I don't even want to know how exactly you're going to satisfy it, but just are they satisfied or not, kind of questions.
I got you.
Perfect. Thank you so much. Great questions. Wonderful. So now the question is that, yes, we have proved the hardness side of it in the sense that LPs cannot do better than half approximation for cut and die cut. We kind of showed that streaming also cannot do better than that. But can streaming do as good as LP? So that's a good question for max die cut because cut, again, it's very trivial, just uniform random partition. You don't even have to look at the edges. But for die cut, can we achieve half approximation in little O of n space? Now, turns out you can, but with a caveat. What we know right now is that for so-called bounded degree graphs, where let's say there's some fixed constant, say 100, if I tell you every vertex has at most incident to 100 edges, then there is a half approximation algorithm that can solve max die cut. And for the half approximation algorithm itself, our idea is that there is a distributed algorithm. We basically take this distributed algorithm and show that it can be implemented in streaming in little O of n space. That's the high-level idea. But now let me define what a distributed algorithm is. Just wanted to motivate it before I go ahead and define it. The distributed algorithm, the idea is that your underlying graph, forget about the directions on the edges and stuff like that, just your underlying graph defines some topology of a communication network. Okay? So this is just after removing all the directions, this is a communication network. Imagine every vertex being replaced by some computer or some node. Now, all the vertices are just allowed to communicate with their neighbors. And what happens is that you have multiple rounds of communication. And so let's say in my first round, I can talk to my immediate neighbors. And if, let's say somebody is at distance 2 from me, they want to send me a message, that would take 2 rounds of communication because it has to go to a common neighbor of us and then come to me. And if someone is distance 3 away from me, it will take 3 rounds of communication. So distributed algorithm, basically, the definition itself is just every time you just communicate with your neighbors, but you can understand that over time, it's not just the neighbors you're communicating with, but you can also communicate with people farther down the line. Just depends on how many rounds of communication the distributed algorithm is using. That's a high-level idea. So what is a distributed algorithm doing for the max die cut problem? So I said every node or this computer corresponds to a vertex. In the end, it just computes some fraction, some number between 0 and 1. And later, it does this rounding, where you just round. When I say rounding, it basically says that with this probability P sub B, place the vertex in the red set, and 1 minus P sub B, place it in the blue set. That's what I mean by rounding. And the performance of the distributed algorithm is measured in terms of the expected value of this partition that it achieves using these probabilities that it computes. So this work of Karen, Sensor, Hillel, Levy, and Shachnai showed that with 1 over epsilon rounds of communication for any epsilon, you can get this kind of a guarantee. Think about this as like at least half minus epsilon. So it's a close to half approximation. Just not quite, you're losing some additional epsilon factor. So this is what they showed. Now, when we go from distributed to streaming, again, we're not interested in computing what this solution C itself is, but all we care about is just computing this expectation of this value of C, because like, if we compute this value, then it automatically satisfies the property that it's at least like half minus epsilon of max die-cut, and we'll be happy with that because that gives us a half approximation algorithm. Perfect. So now, our observation is that in order to compute this value, it suffices to compute how these P sub V's, the probabilities, are distributed across these different vertices. And the main observation is that, let's say I take a k-round distributed algorithm. How much information can a vertex gather before computing this value P sub V? It can only gather up to its radius k neighborhood, because we saw that if you want to communicate with your neighbor, you can immediately communicate in one round. But if someone is distance 2 away from you, you take 2 rounds. Oh, sorry, I think I'm almost done. Thank you. So if someone is distance k away from you, you need k rounds. So each vertex can gather information only up to its radius k neighborhood. So this P sub V must be determined entirely by the radius k neighborhood of that vertex. Once we have determined that, all we need to do is just understand how these neighborhoods look like in your graph. And the reason why this works nicely for bounded degree graphs is that your number of possible configuration is bounded. So let's say degree of every vertex is at most 100. You could only have 100 power k possible configurations for how a neighborhood can look like. So once you have this finite number of possibilities, you can define a distribution over them, how they are distributed in your graph, and basically that's what we are trying to estimate, how these neighborhoods are distributed. And the algorithm, once we realize this, is quite simple. You sample a large number of vertices, still little O of n, and then store the induced subgraph, and just empirically estimate the distribution from this induced subgraph. We show that this distribution is like close to the original distribution, and that's how the bounded degree graph algorithm works. And it is possible to extend this to arbitrary graph, but unfortunately right now we know how to do it only using so-called multipass algorithms. And multipass algorithms are these algorithms that are allowed to go over the stream more than once. So previously I said you have this stream and then you're only going over it like once. It makes sense, of course, when you have like live streaming data, there's no way you can actually do multiple rounds over it. But there are situations where it is actually useful to consider such multipass algorithms. For example, again, let's say you're trying to read from an external memory. It's much more expensive to do random access through that memory compared to like doing some kind of sequential access. So you can imagine that instead of like doing a random access algorithm, you could like run a multipass streaming algorithm where you're again and again accessing the same data in the way in which it's stored, and then this leads to more efficient algorithms. At least that's one motivation to study multipass algorithms. And the results here are that when you allow multipass, we know how to go beyond bounded degree graphs. For example, we give one in our previous work with Singer, Sudan, and Saxena, we have a 1 over epsilon pass algorithm that achieves half minus epsilon approximation. And in an upcoming paper of mine, I show how to get a 2-pass algorithm in little O of n space for max die-cut. So almost there, just we have to get to 1 pass finally so that we completely close that open problem. Okay. All right, I think I'm going to skip over this because this bit. Maybe I can just tell you about the reduction, not how exactly we implement it in streaming. So how would one go about solving something on bounded degree instances to unbounded degree instances? So here is a beautiful reduction due to Trevisan, which is quite simple actually. So I think it might be useful for you guys in general. So his idea is the following. Take any arbitrary graph, unbounded degree. Now what he does is that for every vertex, he creates degree v many copies of that vertex. So this vertex has degree 4. So he creates 4 copies of this vertex, 1, 2, 3, 4. Then on the edges also, he creates some, ignore this parameter, this is just chosen so that it works out in the way we want it to work. But just imagine you take some copies of each of these edges. and then he randomly directs these edges to one of these copies. So you take this edge and then find a uniform vertex among this and just make that edge incident on this. The idea is just that, so originally you began with degree v times d many edges, but one vertex. But now you have degree v many vertices to spread them across. So on average, you don't see any vertex getting more than d edges. So this way, you start with an unbounded degree graph, but you can reduce it to get a bounded degree graph. And he also shows that this reduction preserves this max Tolkien value up to some whatever additive error we want. Max degree is order d, and you can generalize this technique to all kinds of constraint satisfaction problems. Okay, and now, so our high-level idea is just the following. You want to do this reduction somehow. Whatever I described now is a global reduction on using a polynomial time algorithm. But somehow we want to do this in the streaming way, and we want to do this reduction and run the bounded degree graph algorithm on this reduced Trevisan graph, so that you start with an unbounded degree graph. You don't know how to handle that, but do the Trevisan reduction, get a bounded degree graph, and then apply the existing streaming algorithm on this bounded degree graph. That sort of is the high-level idea, but there are a couple of challenges with this. One is that, notice that the number of vertices in Trevisan graph could be really huge, because corresponding to every vertex v, he creates degree v many copies. So even if you have n vertices to begin with, in the end you end up with m vertices, where m is the number of edges, because the sum of the degrees of vertices of a graph is just twice the number of edges in the graph. So if I just blindly do Trevisan reduction and apply the algorithm, what I would get is a little of m space algorithm. This need not be little of n, because let's say m is n squared. If I apply this algorithm, then I'm still not in the domain of whatever space I want it to be. And the next issue is that Trevisan reduction is not really a streaming reduction. So we need to figure out how to do it in a streaming manner. So I don't think I'll have time to explain the second challenge, but the first challenge is easy. I've made slides for the second challenge, so if anyone is interested, I'm happy to go over it later. And this again ties down to your question of how do we do graphs that are much bigger? And this work answers that. It says that, so this is a work of Bhaskara, Daruki, and Venkata Subramanian, where they show that if you have large dense graphs, say m is at least n to the 1 plus delta, then there is a 2-pass algorithm that actually achieves 1 minus epsilon approximation, as good as approximation you want in just n to the 1 minus delta space. So there are a bunch of parameters. Let's fix delta to be 1. Okay, so that is when you have very dense graph with n square edges. What this thing is saying is that you can actually just in polylog space compute a 1 minus epsilon approximation when your graph is super, super dense. So we basically, what we can do is that, so you sort of simultaneously run this algorithm and the separate algorithms when the graph is not super dense. When the graph is not super dense, Trevisan reduction works and the space and all that is fine. And in the end, you can, end of the stream, you could have a running counter for number of edges you see. Then you will know which case is actually the right one. So choose the output of whichever is the correct algorithm. In the beginning, you don't know what's the right algorithm, but in the end, you will know which is the right algorithm. Okay, I'm not going to talk about handling challenge 2 because it's a little bit more complex and I don't think I have the time for it. So I'm going to skip over this. But just wanted to say that challenge 2 can also be handled. It's just that we don't know how to get even further, reduce it to a 1-pass algorithm yet. But that's the open problem. And here's our conjecture. A conjecture is basically that all these are equivalent. Constant round distributed algorithms, LP relaxations, and streaming approximation in little of n space, all of which should give the same kind of approximation factor for CSPs is the conjecture. Sorry, my hairband is not working like that. What do we know so far? So there is this paper of Yuichi Yoshida, which shows that this is in fact true for bounded degree instances. You can solve the LP relaxation of any bounded degree instance using a constant round distributed algorithm. And our paper shows that, again, if you have bounded degree instances, you can simulate a constant round distributed algorithms in little of n space. And then this current work with Madhur and Nova show that LP relaxation is stronger than streaming in little of square root of n space. Our goal is to improve this till little of n space, then that would at least complete that direction. And on the algorithmic side, as I mentioned again, we have a 2-pass algorithm now. It would be nice to get a 1-pass algorithm, then that would complete this direction over here, and also, of course, generalizing to other CSPs. I also want to mention there's another concurrent work in the multipass setting where they actually close some of these directions in the setting. For example, they showed that for arbitrary graphs, you can start from a constant round distributed algorithm and get a order 1 over epsilon square passes log space algorithm. And they also showed that this algorithm is kind of optimal in the sense that it basically achieves the same approximation as LP relaxation. On the other hand, if you want to beat the LP relaxation factor, you would need at least like n to the 1/3 over k space or something. So in multipasses, kind of like this is all that you can do, but it still doesn't answer single pass because if you substitute k equal to 1, it only says that in little of n to the 1/3 space, you can't beat LP relaxation. R shows that in little of n to the half space, you can't beat, and ideally it should be n space itself. But yeah, that's all. Some more interesting open questions. Mostly I was talking about like approximability of CSPs in terms of like how many constraints they can satisfy and stuff. We could also talk about the decidable version where, as I said before, you're given a bunch of constraints, you want to ask how much space do I need to decide whether this is actually satisfiable or not. So this is an ongoing work with my intern here at TTIC, Amatya, and that's one question. Another thing is like, there's another interesting question now. It's like, we know that up to certain points, streaming algorithms and LP relaxations are equivalent, but can we actually like, let's say beat half approximation using extra rounds or more passes? And this kind of study, like whether can we beat half approximation for max cut or in general LP approximation for CSPs, could plausibly lead to like general polynomial time algorithms that lie somewhere between LP and SDP. And this also sort of answers your questions in the sense of like, if maybe we have a richer literature of like what can be done between LP and SDP, you have sort of more choices in terms of like what kind of approximability you're looking for versus the time you're willing to spend on achieving such an approximation. Finally, we could also think about finer characterizations. For example, this work with Chining Chow, Sasha Kulevnev, and Madhusudan, we characterize optimal approximation between like log cube space versus square root of n space by a much simpler local algorithms, not distributed algorithms themselves. So could we get such finer characterization in this whole domain? That's it. Thank you for listening. But first, I want to give a special sort of thanks to TTIC itself. And as Avram mentioned before, I'm actually, moving out of TTIC next month, and I'm like super, super sad to do that. But I wanted to just thank Avram for all your support. Thank you so much. The last 2 years have been fantastic, and thanks for, I guess, everything. And then I really wanted to thank our administrative assistant, Mary Mar, who's been like amazing in like helping with all the paperwork. I mean, without her, I think even now I probably would be swamped with a bunch of paperwork. But she's really efficient, takes care of everything. And I also want to thank Madhur. He's been a fantastic mentor, and I couldn't have asked for anyone better. I also wanted to thank other people who support, I think, on a day-to-day basis: Amy, Alice, Adam, Derry, Brandy, Rose, Randy. I'm sorry if I missed any names, but thank you so much. Thanks for everything, and thanks to you all for listening. Yeah.
Question?
The square root of k lower bound you mentioned, is that for just max cut or is it for any CSP?
The square root of n or?
Square root of n, yes, sir.
A square root of n is for any CSP.
Okay.
Yeah. LP relaxation for any CSP is stronger than streaming in below square root of n space.
And about putting the assignment as well. So order n by sampling is just the value.
I think you could also potentially output assignment because like if you have very high degree vertices, which really make a difference in terms of like where they are placed, you're very likely to be able to find what they, like you can solve the max cut problem on the sampled instance, and for high degree vertices, you will be able to know exactly where you're supposed to place them. But for low degree vertices, you might make mistakes, but I don't think that matters at all. I think it is possible, though I haven't worked out the details, but I thought about it some time ago and it seemed like it's doable. Very good question.
This might be my last question.
Please ask away.
So, my whole thing I'm thinking is, like, what's the real, like, I call it that research you're doing with all of the different algorithms. Like, the streaming algorithm, the max cut, and like, I can with that. So, my thing is, like, I mean, I can kind of think of, like, the applications. So, I'm just like, what's a concrete application that you can think of that you can apply to, or some of that? Maybe like the streaming algorithm, for example, because that seems like a really big one, right? With like networks, even like streaming services like Netflix. Because I know like streaming is kind of a problem, especially when there's a lot of traffic over the network. So is that like an area you can apply all of that to?
I think that's a very good question, and though unfortunately, like I don't know of a concrete application because I haven't yet collaborated with somebody on the other side, the applied side, who knows kind of like where exactly it should be applied.
I'm studying software engineering, so for me, like I constantly think about
That's really good. I think that's something I definitely want to think about in the future. Right now, I mean, I do imagine seeing applications, like distributed algorithms I know are already applied, like for CSPs. So streaming algorithms, I think the challenge is just that the application really has to be something where, so for example, I could imagine this where, let's say, should I take this offline or is it okay time-wise? Okay, let me just finish it. So I think one thing where, so a distributed algorithm differs from a streaming algorithm is that in a distributed algorithm, you're still actually computing the cut itself. Whereas in a streaming algorithm, you're only estimating what the value of the cut is.
Oh, we were talking about the radius where the distributed algorithms to like cross communicate over.
Yes.
I was kind of confused about that a little bit. Like, how does that work?
So I think this I can probably take it offline and explain. Just didn't want to hold up people for lunch, but yeah, I'm very happy to answer that. Let's take it offline. Thank you so much. Thanks everyone.
Thanks.